Hello guys, now we go for the implementation of our first interior point method. So probably you guys remember from the previous video that we developed together an interior point method to solve a linear optimization problem. That's of course a problem that was based on a book chapter. I provided the reference in the previous video and all the details. Now I want to show you a source code I wrote in R, the R statistical software, and of course compare my code with the formulation so you guys can understand what's happening behind and understand the details and everything. So let's go for our problem. Here is the problem. Of course, we have the primal problem and the dual, or its dual, yeah. Of course, here we have a graph in terms of the primal space, and here in terms of the dual space. Here I have x1 and x2. Here we've got pi1 and pi2 as our variables, okay? So this is our objective function, the primal problem, 2x1 plus 3x2. Here we've got the objective function for its dual, 8 pi1 plus 6 pi2. What is important here is, of course, this is one way of writing the problem, and this is a complementary way of writing our problem. What we are going to do is we're going to consider both problems together, combined, okay? So we can understand how a step towards the solution of the primal affects its dual. That's what's going to happen with our code over here. And these are our constraints, 2x1 plus x2 plus some slack variable x3 must be equals to 8. I think you guys remember this is a slack variable from the previous video. x1 plus 2x2 plus another slack variable x4 must be equals to 6. So those two were small as less than or equal to operators, and then we changed both to be solved in terms of equalities. That required, of course, slack variables and positive slack variables, as you guys can see over here. And the dual problem is like this: 2 pi1 plus pi2 minus z1, that negative sign over here in front of some positive, some semi-positive, I should say, because it's greater than or equal to 0. z1 is equal to 2. That happens, again, because here we had an operator greater than or equal to. So we have to remove some unities to make it equal to 2. The second constraint, pi1 plus 2 pi2 minus z2 is equal to 3. The same happens here. So as discussed in the previous video, guys, pi1 and pi2, I just decided, actually the book chapter considers that we are going to substitute pi's by z1, z2, z3, z4. So pi1 is going to be equal to z3 and pi2 is going to be equal to z4. That's why when we remove z3 units from pi1, it becomes equals to 0, and pi2 equals to 0, okay? And all those z's must be greater than or equal to 0. Sorry, my dog, oof, again, she's terrible. So this is our prime space, this is our dual space. So I will start with some solution over here and walk towards the optimal for the maximization in this space. And here walking towards the optimal like this in order to minimize, of course, the final result obtained applying this point into my objective function of the primal problem is going to be very close or equal to this point, 1/3, 4/3, applied into my optimization problem in the dual form. Okay, so this is my problem. We have to ensure some things over here, but actually I prefer to discuss with you directly on the code. I'm going to use two R libraries, Mass and LinSolve. This one is to solve linear systems, and this one helps me to find inverses, matrix inverses. Actually, other operations too, but in my case, I'm just going to use for inverses. As you guys can see, this vector C has the values, the coefficients for the objective function. Let's note here the primal objective function. Take a look at the primal objective function. 2x1, 3x2, 0x3, and 0x4. That's why it is 2, 3, 0, 0. I just decided to create a matrix to represent this with a single row. That's of course the same as a vector, a transposed vector. Okay. Here we've got our coefficients, our constraints coefficients. Okay. Take a look at the coefficients. 2x1, so we've got 2 here. 1x2, that's why I've got 1 here. 1x3, that's why I've got 1 here. And 0x4 for the first constraint. And the second constraint is going to be 1, 2, 0, and 1. 1, 2, 0, and 1, 0, because we have no x3 over here. Okay? And the coefficients, the upper bounds, actually the equality bounds we've got now for our primal problem are 8 and 6. Also organized now as a column vector, as you guys may notice. This is a matrix, okay? The coefficients are in a matrix. So the next step we must take is to define our first solution, our candidate solution. Here, I could have decided to select, for example, x1 and x2 having like a different value, since the value, of course, making sure the value are accepted by our problem. So x1 and x2 must be greater than or equal to 0, and those two constraints must be satisfied. So in this scenario, take a look. I decided to select x1 equals to 1. I'm going to write for you here. x1 equals to 1 and x2 equals to 1 as well. So both are greater than or equal to 0, as they should be. Of course, constraints must be satisfied. Take a look here. 2x1, 2 times 1 plus x2, which is also 1. That's going to be 3. So I must sum up something to make this equals to 8. And this something that I must be summing up has to be greater than or equal to 0. Of course, I cannot subtract something. So in this case, x3 is going to be equal to 5, as you guys may notice here. And the second constraint must be satisfied as well. That is 1, x1, and that's just 1, plus 2 times x2, which is 1, 2. So that's going to be 3 plus something, that's of course 3 to be equal to 6. That's why we have this 3 over here, and that's why x4 is equals to 3. Okay? And the z's are going to be defined in this diagonal matrix. You guys can notice I'm using diagonal matrices here. I could have used like something different, just like a vector, of course, but I decided to use as a matrix. because I think I need to, compute the inverses of z and x, and it's easier if they are diagonal matrices, of course. That's why, okay? So z1, z2, z3, and z4. We know z3 is equals to pi 1. That's why this is equals to 0. And z4 is equals to pi 2. That's why this is equals to 0. So you guys can notice that pi 1 is 2 and pi 2 is 2 as well. So we decided to call pi 1 is of course equals to z3, and this is equals to 2. I just use this number. You can change it if you guys want, okay? And pi 2 is going to be equal to z4. And of course, I also decided to call this, to define, to assign 2, okay? Then we've got, of course, z1 and z2. So I'm going to write both. Over here, z1 is going to something, it's going to be equal to something, and z2 equals to something else. Take a look here. If I define pi 1 as 2 and pi 2 as 2, so I will have 2 times 2, okay? 4 plus 2, 6. 6 minus something. See, 6 minus 4. That's why I've got 4 here for z1. If my constraints are not satisfied, I cannot proceed. z2, take a look here, 2 plus 2 times 2. This is going to be 6 again. 6 minus 3 is going to be equal to 3. That's why I've got 3 here, okay? Quite easy. And then here, I just defined the pi values because I will need those later. So I just decided, okay, let's call like some matrix pi and use pi here just to make this easier for some operations, some mathematical operations I need to employ later. Here I am defining me. I think you guys remember this me. This is actually the importance will be given to the boundaries, to the barriers, to the log barriers. You guys remember probably. And again, here we've got a1 vector. This is going to be basically like a vector containing 1, 1, 1, 1, 4 times. 4 times because I need to apply this as I need to multiply this by the column space of matrices X and Z. That's why. Here I just defined like some steps I'll be given. This is not important for now. I will explain later. This is not important for now either. I will explain later. Here I just decided to count how many iterations we've got. That's all, just as a piece of information, okay? Informing the number of iterations, okay? Quite easy. This is a threshold. A threshold to define the stop criterion. That's basically a way of assessing something we call the gap in between the primal and the dual spaces. Okay, so we are measuring how different the solutions are if we compare the primal solution with the dual solution. That's the same as taking, what is the solution? What is the objective function for this point? It's going to provide something here. And for this correspondent point, it's going to provide something else over here. Is that applying this objective function very different from this? Yes, so carry on. And of course, I'll be walking on the gradients. And then when I am really close to this point, which has the solution for me, those two objective functions will provide very, very close results. You guys probably remember this. This is our complementary slackness. Complementary slackness. The Karush-Kuhn-Tucker third condition. Okay? The third condition, third Karush-Kuhn-Tucker condition. That's where we define how close we are when we compare the prime and the dual spaces. You guys you can go back in the other videos and see that in some formulations I used S as slack variable instead of Z. I just use Z here to make sure we follow the same principles of the book chapter. But of course it could be S, and if you guys go back, S multiplied by X must be equals to 0 to ensure something we call strong duality. Strong duality means the primal space, when I try to solve it, I have the same solution in terms of my dual space. That's quite nice. And this is like this. While the gap, or while the difference in between the solutions provided by the primal and the dual spaces are different enough, and the threshold is going to be defined how enough, of course, okay? Carry on with the optimization process. Quite nice, isn't it? Yeah, easy to understand what's happening now. I hope, of course, giving like all possible details I can for you guys. So I hope this is understandable. Of course, here we are going to see how many iterations, just to know what's happening. And all those over here are the equations we found together in the previous set of slides. I can just open the previous set of slides for you. Take a look over here. I think it's class, oh yeah, it's like this. Class 8, 31, Convex, PDF. It is here, so let's remember. You probably remember this, guys. If I go to the end, those were the equations we found together. Take a look at the equations. They are here. So I just defined those equations here. Actually, those three are exactly the equations. So I'm going to write for you here, equations found after our formulation. Remember, what was the formulation? The Lagrange, actually, we differentiated the Lagrangian functions for the primal and the dual problems, and we found this all together. If you guys take a look, all this function g-inv or inversion is a function to provide the inverse of a given matrix. So if I come up here, and of course I require mass, I have access to g-inv, which is the inversion of a matrix. So if I've got like, okay, we have like some matrix here. It's going to be a matrix whose mean is going to be equal 0, standard deviation. I will have like 3 rows and 3 columns. Oh, what's happening? Oh yeah, times 3. So this is a matrix. What happens if I take this matrix and apply G inverse on A? It's going to provide the inverse for me. So if, of course, I apply once more, I I get back to A, as you guys can see over here. Just compare, pause the video and compare, okay? So that's what I'm doing here, computing the inverses. A, product by the inverse of Z, as you can see here. Product by X, as seen here, and product by transpose, A transpose. And all that inversed. That's why there is an inverse over here. Remember, this is the matrix multiplication and also the dot product symbol, okay? Minus B, as in here, plus me A Z inverse, plus me A Z inversed, and of course, the multiplication, actually the product by our vector with ones, plus AZ inverse X, and something that I called this F of pi, I just decided to call it like delta D over here. And delta D is defined here. Take a look. That's also that's our delta D. You guys may notice that my delta D was defined here. Okay, that's the transpose, A transposed, pi transposed, or D pi as I define here. Okay, and take a look at my initial delta for pi, or my initial variation. The initial variation I will consider for pi, I will consider 0 as my initial variation. I'll have here a vector 0, 0, no variation. And what is the variation for Z? It's also going to be 0, 0, 0, 0, no variation at the beginning. Okay, so actually here, and there is something that I could add up here, which is minus this C transposed. It is not in here, but we can add up later, no problem. So we can just see what happens with C transposed over here later. No problem for now. So now I just decided to compute DZ, which is in here, as you might notice. That's minus delta D, which is in here, okay? Minus delta, and plus transpose of A transpose, sorry, D delta pi, and delta pi is here, and delta pi, of course, at the beginning is 0. And here we've got dx, and dx is transpose Z transpose, me product, of course, by some me product by a vector of ones. This doesn't matter the order over here, of course, okay? Just decide to write like this, but it could be the opposite, like me product by E, doesn't change anything. Minus X product by Z product by our one vector with ones, of course, that's why we call like one vector, okay? And minus X product by DZ. I just want to go back with you guys, remember DZ here with zeros, okay? You can notice I haven't defined dx, delta x, because just delta pi and delta z, because dx is going to be computed over here. Here I came up with some like ideas of trying to walk towards a gradient in just slowly. So I just came up with this idea of adding like variables to define the steps I would give towards a gradient. So I just came up with some idea here that comes from that book chapter. They discuss at the end some possibilities on how to change. It's not really important to discuss this at this point. You're going to understand when you guys see this. take a look. What's going to happen with my x? My x will receive itself plus some adaptation given by delta x. So this is the amount or the step actually I will give towards the gradient in terms of adapting x. This is just a variable that when multiplied by my delta x walks, but walks less. That's the same as defining. If you guys want to define this as 0.1, I'm going to walk like 10% of that towards my solution and not like everything towards the solution. If I try to walk everything that's possible towards the solution like this, sometimes it happens that we cross the boundary. We cross the log barrier, and that's not interesting. That's not desirable. That's why I came up with this idea of defining some step. And this is the way I define the step in some sort of adaptive way. So I just said, okay, let's try something that's written in that particular book chapter. You guys can either read the book chapter, or you can just come up here and set like 0.1. It's going to work. Something that's smaller than 1. It could be even like 0.99. It's going to work. But yeah, just decide to define some step to adapt the gradient. That's like the gradient descent method. So if you guys remember, go back into some calculus book and look for the gradient descent method. That's what we have been using here. We're adapting x in terms of the gradient descent method. The same happens here for pi, and the same happens here for z. Why I am using the diag of this matrix transformed in a vector, as you guys might notice, because here, this is actually a vector. I'm just ensuring it is a vector because, you know, R has like some problems with types, so I prefer to make sure this is a vector, and then I transform it into a diagonal matrix to sum up with something that is a diagonal matrix. Otherwise, I cannot sum up. Okay? Pi is not a diagonal matrix. As you might notice, here pi is a vector. That's why I could sum up pi directly like this. But z is a diagonal matrix, so I had to transform my vector into a diagonal. What I'm doing there is basically this. Transform this into a diagonal matrix. So it transforms my vector into a diagonal matrix. Quite easy. Okay? Here, once more, I compute the gap. Why? To make sure that I have to carry on computing or not. Basically that. Okay? If I need or not carry on computing. Just something. Here it's minus, and here we've got f of x, f of pi, and f of z, okay, inside. That's why sometimes we have the minus sign over here because of this change. That's going to bring like some minus. Sometimes it's not minus, it's plus because of the solution we found together, just to make sure, okay? Then there is something I didn't tell you before. There is a need of reducing me. Actually, we need to reduce me to get closer to the barrier. So by reducing me, we just make sure we are getting closer to the barrier if necessary. So how I decided to define me? Actually, I set up like some me at the beginning, and afterwards I just decided to use like, I'm going to use the gap or the difference I have in my solution in spaces, of course, in terms of the prime and the dual, divided by some counter powered to 2. This could be different. I could just decide, okay, me is going to be itself minus, or like itself multiplied by 0.9. so I'm going to reduce it like 10% per iteration. It's going to take more iterations eventually, but it works as well, okay? I think there is like some, yeah, I need to consider this minus C transposed over here. Yeah, that's all I believe, yeah. And counter is going to be counter plus 1. And then I just decided later, take a look at this. This is quite interesting. After solving this, I said, okay, let's just see what happened with our constraints. This is the constraints we have for our primal problem. Take a look. A is a matrix with all those coefficients. And I will multiply that by our vector x. Here is a vector because it was a diagonal matrix like this. Take a look. If I apply the diagonal function again, it's going to be a vector. So it gets me back the vector. When I apply a multiplied by x minus b, it must be equals to 0. Minus b is the same as minus 8 and 6, of course, which were defined at the beginning. And for this, take a look again. I think you guys remember that's going to be the A transpose, the transposition of matrix A multiplied by pi minus the diagonal Z minus the C transposed. This is actually a result we found together. Getting back, we found together in our differentiation of the Lagrangian function. Going back, let's go. Oh, it is in here. Take a look. A transpose pi transposed, okay, minus Z. It's not necessary to transpose because here it's just a vector, okay, minus Z minus the C transposed. That's why I've got this, okay. That's why I've got this. That's really, really nice. And then, of course, the last one, which is this, the me complementary slackness, which is how connected both solutions are. Diagonal of x multiplied by z minus me must be also 0, because that's going to show me the me complementary slackness. As you guys might notice, those are our primal constraints. Or if you prefer, what is the name? The first Karushkin-Tucker condition. Okay? Those over here are going to be our dual constraints. Let's do like this, okay? Dual constraints. Or dual feasibility, if you prefer. Second Karushkin-Tucker condition. And this is called the me complementary slackness, or the third Karushkin-Tucker condition. What connects? This is responsible for connecting the primal with, let's go there, with the dual space. Okay? The primal with the dual space. Or maybe like this would be better, right? Connecting the primal space with the dual space. It's a bit like verbose, but it's okay. And then I decided to print out x and print out z. Inside z, we're going to have pi's, okay? I'm going to run like this, and then I make the change. Take a look. After 11 iterations, our gap is really, really small. Something multiplied by 10 to minus 5, 10 powered to minus 5. Results for the primal constraints, almost 0 and almost 0 for these two constraints. Really close. And for these 4 constraints, wow, 0 and 0. And here, really close to 0 and really close to 0 for the 2 first constraints. Okay, and the other 2 here, really 0. Yeah, pretty much. Those were the complementary slackness. Okay? 0, 0, almost 0 for all four. Remember, all four. Why? Because we are multiplying the diagonal of x by z, which is a vector multiplied by z. This is going to produce like 4 results for us because we've got 4 z's. Minus me, so 4 results. Take a look at the diagonal matrix X. I just apply diagonal at that matrix and I will have X1. That's the solution for X1. Take a look. 3.333. That's 10 divided by 3. X2 is going to be 1.333. That's 4/3 as shown here. What is the value for X3 and X4? They are very close to 0. Very close to 0. They're almost 0. Those are our slack variables. That's a numerical 0, of course. Dual problem, Z1, very close to 0. That's great, because that's a slack variable. Just showing us that we are getting close to the vertex. Z2 also close to 0. Perfect. Z3 is going to be 1/3, as you might notice, 0.333. And Z4 is going to be 1.33, that's 4/3. We found the solution. Great. So what I should do now, actually, I should have written something like this, minus the transpose of C here. I think I forgot that. I don't remember, but I think I forgot that. Yeah, I forgot, but that actually changes my space. I remember there was like something connected to this. Let me confirm for you guys. Yeah, actually, this is interesting to mention. I remember this, if I add up this at the beginning, it will change my solution. Actually, there is a trick over here. When I compute this, I better not use C transposed over here because I depend on the values of delta pi and delta z, and I could make the solution invalid. Actually, after some operations, this is going to be corrected. So just getting back, I just did not use this. If you guys go to that book chapter, you're going to see that this works as a trick to solve our problem. It's going to find the solution in any way, but don't use this C transposed over here when you solve your problem. It's not even necessary. I just removed it, okay? There are like some foundation on that, why we can remove it and still find the solution. Actually, I don't really remember at this point, okay? But I remember I did that. I did that, and people, like even the book chapter, recommends that. That's just an additional step. So every time you are using this algorithm for solving a problem, just don't consider the coefficients for your primal objective function. That's all. The rest is the same, just the same. Okay. There are like some tricks on how we should define me. For example, I told you guys, oh, I could here like define like me multiplied by something in order to reduce me. Let's see what happens if I do that. It's going to take like more iterations, as you might see. The results are pretty much the same, but I will take like more iterations. So I just decided to use like something that I remember, that I see, of course, in that book chapter. But I could give like just reduce like 1% of me at every iteration, but I will need like more steps, more iterations to find the solution. Okay, that's also possible, no problem. We can use it if you guys prefer. I'm going to leave like this so you guys test it. There is something else I told you guys that I could, instead of using this alpha P and alpha D over here, I could have set this as 0.1, for example. Let's try it as 0.1. So I will walk less towards the gradient, okay? The gradient descent in this case. And that's going to, the solution is going to be the same, but takes like more iterations again. Okay, I just changed like this to something that requires less iterations, but even with this that requires less iterations, it takes more. So if I use me, changing just 1% of me, I will probably have like more than 146 iterations. Yeah, of course, you guys can see here, that takes like 1,000 and some iterations. Of course, I could just remove this and leave the code like this. It's going to take like more time, that's all, okay? I'm going to go back. You guys can change and perform in both ways. I'm going to leave my code in its typical form, like this. The form I decided to rotate, okay? Again, this was a trick. Please read the book chapter to see more details on that. You're gonna see that there are like lots of discussions on this. Actually, pretty much, there are really many discussions on that. It's not that easy to find this kind of like a justification for this kind of trick. Yeah, I know it's a bit, yeah, messy, I know, but no problem. At least it's working. Guys, we're gonna go now for the next video, okay? I hope the solution you found was similar to this one. You notice there are like some tricks to solve, there are some things to define, like steps I will be given towards my solution. That's why I defined those over here. It's not even necessary, okay? I could just change this to 0.99. You see, I decided to employ the minimum of some division. This gives me some idea on how the gradients are changing in my space. And I multiplied that by some alpha 0 to find alpha P and alpha D to perform the gradient method over here. That helps making it faster. That's why I've got the result like with less iterations, like 11. But the number of iterations doesn't matter, okay? You could find a solution using a different approach. That's okay. Guys, see you in the next video.